10. Welcome to Navier-Stokes Equation. This chapter is the heart of fluid dynamics. The Navier-Stokes equation is not just a formula, it is a powerful framework that describes how fluids move. Whether you're modeling airflow over an aircraft wing or predicting ocean currents, this equation is your foundation. But let's not be intimidated by the math. At its core, the Navier-Stokes equation is just Newton's second law applied to fluids. Force equals mass times acceleration. The complexity arises from the fact that fluids are continuously deforming, and we must track this in space and time. In this session, we will walk through the assumptions, derive the equations step by step, and understand where they apply and where they don't. The goal is not just to memorize it, but to truly feel how pressure gradients, viscous forces, and inertia interact inside a moving fluid. Ready to unravel one of the most fundamental ideas in engineering and physics? Let's dive into the flow.
1. Why we need approximations in fluid mechanics. Let's begin with a truth. The Navier-Stokes equations are powerful but brutally complex. They describe the motion of Newtonian fluids, assuming constant fluid properties, but solving them exactly is almost never possible in real-world situations. That's why approximations are not just helpful, they are essential. Exact solutions exist for only a handful of idealized cases. In real life, we rely on simplifications and numerical models to make progress. We introduce 4 common approximations to reduce this complexity. Creeping flow applies when inertia is negligible compared to viscosity. Think of honey slowly moving through a pipe. Inviscid flow ignores viscosity entirely, useful for high-speed flows far from solid surfaces. Irrotational flow assumes zero vorticity, often valid in regions where the fluid is undisturbed by boundaries. Finally, the boundary layer approximation focuses on thin viscous layers near walls where most of the velocity change happens. Each of these approximations is a lens, allowing us to simplify the equations without losing essential physics. In this course, we'll learn how and when to apply them.
2. Why we use non-dimensionalization. Before we dive into solving the Navier-Stokes equations, let's step back and simplify the problem by removing units. Non-dimensionalization helps us rewrite the continuity and momentum equations in a cleaner, more general form. This makes it easier to compare different flows and identify what really matters. The power lies in the dimensionless numbers. Each one tells a story about competing forces in the flow. Reynolds number compares inertia to viscosity. Dominate inertia and you can ignore viscous terms. Euler number tells you whether pressure or inertia drives the motion. Froude number compares how gravity stacks up against inertia, key for open channel and wave flows. Strouhal number shows how important unsteadiness is compared to convective acceleration, vital for oscillating flows. These numbers aren't just academic. They tell us which terms in the Navier-Stokes equations can safely be neglected. In practice, they help engineers make smart approximations, guide experiments, and design efficient simulations. The equations stay the same, but their dominant physics shift depending on the values of these dimensional parameters. That's the real utility of non-dimensionalization, revealing the flow's true character.
3. Understanding creeping flow when viscosity rules. When the Reynolds number is much less than 1, inertia takes a back seat and viscosity dominates the flow behavior. This is the world of creeping flow, slow, highly viscous motion where the fluid glides rather than rushes. You see it in the slow ooze of honey or lava, or in the microscopic realm as bacteria swim through syrupy fluid. At these low Reynolds numbers, the density, rho,
becomes irrelevant and drops out of the equation entirely. The Navier-Stokes equation simplifies dramatically. Pressure gradients balance directly with viscous diffusion. Mathematically, we reduce it to grad P equals mu del squared V. This simplification unlocks analytical solutions for situations like the drag on tiny spheres. Stokes' law gives us the drag force, Fd equals 3 pi mu Vd. This is foundational in predicting the terminal velocity of particles, such as volcanic ash, or calculating the resistance on airborne pollen. In creeping flow, we learn how important viscosity can be. It's not just about high-speed jets or turbulent wakes. Sometimes the slowest flows are the most elegant to analyze.
4. Inviscid flow, when inertia takes over. What happens when you move fast enough that viscosity becomes negligible? Welcome to the realm of inviscid flow, where inertia dominates and the sticky effects of viscosity fade away. This happens when Reynolds number is much greater than 1, typical in high-speed or large-scale flows. By neglecting viscosity, we arrive at the Euler equation. dV dt equals minus 1 over rho nabla p plus g. This form is elegant and much easier to solve than the full Navier-Stokes equation, making it attractive for modeling idealized flows in aerodynamics and hydrodynamics. Inviscid flow is useful when analyzing regions far from walls, such as the bulk of an airflow around an airplane or deep inside a water jet. But it comes with limitations. It cannot predict drag, nor can it handle boundary layer behavior. In fact, it leads to D'Alembert's paradox, a theoretical result that suggests there should be zero drag on a body in steady, uniform, inviscid flow. We know that's not true in real life, but it shows how idealizations must be handled with care. Use inviscid flow for simplicity and speed, but always remember what it leaves out.
5. When flow has no spin, irrotational approximation. In some flows, the swirling motion, the vorticity, is so small that we can consider it zero. This gives us the irrotational flow approximation, where omega equals del cross V is negligible. Once we make this assumption, something beautiful happens. We can define a velocity potential function phi that satisfies Laplace's equation, del squared phi equals 0. This shift turns the problem into one of potential flow theory. Instead of solving complex nonlinear Navier-Stokes equations, we solve Laplace's equation, which is linear and much easier to handle. It allows us to build flows by superimposing simple solutions like sources, sinks, and vortices into more complex patterns. But the real gift of irrotational flow is Bernoulli's equation. If the flow is irrotational everywhere, then Bernoulli's equation holds throughout the entire field, not just along streamlines. That means P over rho plus V squared over 2 plus GZ equals constant is globally valid, simplifying analysis and providing direct links between pressure, velocity, and elevation. Irrotational flow may not be realistic near boundaries, but in regions of smooth flow, it is a powerful approximation. It simplifies math without losing the essence of the physics.
6. Boundary layers, where fluid flow meets the wall. In high Reynolds number flows, something special happens near solid surfaces. A thin region forms, the boundary layer, where the fluid velocity transitions from 0 at the wall to the free stream velocity. Outside this thin layer, the flow behaves as if viscosity doesn't matter. But inside, viscous effects dominate. This leads to a powerful simplification. We divide the domain into two regions: the outer inviscid flow, where Euler or potential flow equations work fine, and the inner thin boundary layer, where the boundary layer equations apply. These equations assume that pressure is nearly constant across the thin layer and that streamwise acceleration is far more important than vertical acceleration. The boundary layer approximation tells us a lot. It helps us estimate drag on objects, predict boundary layer thickness, and calculate heat transfer near walls. A classic estimate gives delta approximately x over the square root of Rex, showing that the boundary layer grows downstream but remains thin. This approximation is essential in engineering. Whether you're designing an airplane wing, a race car, or a heat exchanger, understanding boundary layers is critical. They may be thin, but their impact is massive.
7. Building complex flows from simple pieces. One of the greatest strengths of potential flow theory is its simplicity and its flexibility. Because the governing equation, Laplace's equation, is linear, we can superimpose solutions to create new, more complex flows. This is known as superposition in irrotational flow. We begin with elementary flows. Uniform flow gives us a constant background velocity. Sources and sinks produce radial flows, outward for a source, inward for a sink. Vortices add swirling motion, and doublets combine a source and sink very close together, giving rise to symmetric flow patterns. By combining these elements, we construct useful models. Add a source to a uniform flow, and you get the Rankine half-body, an idealized shape with a smooth front and a wake. Replace the source with a doublet, and you create flow over a circular cylinder, capturing essential features of bluff body flow without the complexity of solving Navier-Stokes directly. This method doesn't predict drag or separation, but it gives engineers a powerful toolkit to visualize flow patterns, design streamlined shapes, and understand the interaction between flow elements. Think of it like building with Lego blocks. Each block is simple, but the possibilities are endless.
8. Perfectly circular flow, imperfect reality. When we superimpose a uniform flow with a doublet, a closely spaced source and sink, we get a classic result in potential flow: flow over a circular cylinder. It's elegant, mathematical, and visually satisfying. The streamlines form a perfect circle, wrapping symmetrically around the object. At the cylinder surface, the velocity varies with angle, given by v equals 2v infinity sine of theta. This means maximum speed at the top and bottom, theta equals 90 degrees, 270 degrees, and zero velocity at the front and rear stagnation points, theta equals 0 degrees, 180 degrees. The pressure distribution follows smoothly, as Cp equals 1 minus 4 sine squared of theta, with high pressure at stagnation and low pressure where velocity peaks. But here's the catch. This model predicts zero net drag. According to the math, the forces balance out perfectly. This is D'Alembert's paradox. In reality, objects like cylinders experience substantial drag, mostly due to boundary layer separation and wake formation, factors that potential flow simply ignores. This slide is a reminder. The mathematics can be beautiful, but without viscosity and separation, it misses critical physics. Use the cylinder model for insight and pressure predictions, but not for drag.
9. When drag drops suddenly. The drag crisis explained. Not all flow over a body is smooth and predictable. When the fluid meets a blunt object, like a sphere or cylinder, boundary layer separation is inevitable. This separation creates a wake, and that wake is the main source of pressure drag. Here's where things get interesting. The nature of the boundary layer, laminar or turbulent, dramatically changes how and where separation occurs. At low Reynolds numbers, the boundary layer remains laminar and separates early, producing a wide wake and high drag. But as the Reynolds number increases, the boundary layer transitions to turbulent. Turbulent flow clings to the surface longer, delaying separation and reducing the wake size. The result? A dramatic drop in drag. This sudden shift is known as the drag crisis. It's counterintuitive but powerful. Rougher or faster flow can actually reduce resistance. That's why golf balls have dimples and why high-speed vehicles exploit surface texture to manipulate boundary layers. Understanding this phenomenon is critical for engineers in automotive, aerospace, and sports design. The flow may look chaotic, but the physics is remarkably consistent. Predict it, and you control the drag.
10. Where Navier-Stokes equations shape the real world. Fluid mechanics isn't just a theory in textbooks, it's everywhere around us. The Navier-Stokes equations underpin how we design, analyze, and optimize systems in every major branch of engineering. In aerodynamics, these equations help shape the wings of airplanes, streamline the bodies of race cars, and guide the design of efficient wind turbines. Every contour and angle is tested against fluid behavior. In hydrodynamics, they govern the resistance and stability of ship hulls and submarine bodies. The ocean is never still, and fluid equations help engineers anticipate its impact. In biomedical engineering, blood is treated as a fluid. Understanding arterial flow, or airflow in lungs, means solving the Navier-Stokes equations for complex, pulsatile, and branching geometries. In chemical engineering, they appear again, inside reactors, pipelines, and mixing vessels. Every transport process involving heat, mass, or momentum draws from the same mathematical foundation. From vehicles in the sky to particles in a bloodstream, the Navier-Stokes equations are the invisible blueprint. Master them, and you understand the flow of the physical world.
11. Master the flow by knowing what to simplify. Let's wrap up with what matters most. The Navier-Stokes equations are the foundation of fluid mechanics, but solving them directly is almost always too difficult. That's why engineers turn to approximations. These are not shortcuts. They're targeted simplifications based on dominant forces in different flow regimes. If viscosity rules, as in creeping flow at low Reynolds number, we ignore inertia. If inertia dominates, as in inviscid flow at high Reynolds number, we ignore viscosity. When vorticity is negligible, we use irrotational flow and unlock potential flow theory. Near walls in high-speed flows, the boundary layer approximation takes over, isolating the thin region where viscosity matters most. Superposition adds flexibility. By combining simple solutions, uniform flow, sources, sinks, vortices, we build up complex irrotational flows. But we must also remember where the models fail. Drag crisis and boundary layer separation are real-world effects that reveal the limits of inviscid and potential flow theory. The key takeaway is not just to understand each equation, but to know when and why to apply it. That's what turns a student into an engineer.